From Chicago, welcome to 3Degrees Discussions. I'm your host, Mike Vasquez. This is a podcast devoted to the stories behind the innovators, entrepreneurs, and leaders in the 3D printing industry.
Yeah, whether you're reverse engineering material, you're doing R&D on something, or you're doing quality control, it's way more important now, now more than ever in the world to really understand the chemistry of the new metals we're making, the new ceramics we're making, or the hybrid of the two.
That was Jeff Williams. Jeff is the founder and CTO of Exum. He's a master's in Cosmochemistry from the University of New Mexico, and during his time as a research scientist there, he became immersed in the challenges of analytical instrumentation. There, he began his entrepreneurial journey to improve the ways in which we understand and characterize materials. Before we get started, head over to www.3degreescompany.com and subscribe to the podcast. Remember, you can listen to the show anywhere you download your podcasts, including Spotify, Apple, Amazon, or Stitcher. Also, if you or your company are looking for materials, qualification, or general added manufacturing support, reach out to the team through our website or via email at info@3degreescompany.com.
All right, Jeff, thank you so much for joining the show today. Excited to talk about your technology and what you're working on. And so one of the things that I like to start out with all the guests and episodes is really get a sense of the person behind the companies and behind kind of what they're working on and your career. So let's go back to the very beginning. Like, where were you born? Where'd you grow up? What were some of those early days like as you kind of got in the path towards where you are now?
Yeah, absolutely. Okay. That's a unique question. Most people start like founding of the company, but we're going back to birth. I like this. So yeah, from Tampa, Florida. I grew up Florida man. Still hold a special place in my heart for Florida, but was ready to get out of there for sure. Yeah, so pretty much from a young kid, I was always like the kid that was taking everything apart that my mom had to hide alarm clocks from and everything else around the house because it would just be in pieces and then I would never put it back together. And so she went through a lot of alarm clocks. Then, kind of going into high school started building my own cars at the age of 15, or started out with lawnmowers and jet skis and anything I can get my hand on to tinker with and play around. I never really had this story in my head that I was good at engineering, science, math growing up. I went to an all-boys Catholic school and was kind of like the rebel atheist and was more focused on that than I was on math at the time. But going into college, I started creating an appreciation for geology. I was a big climber through high school and then into college, and pretty much that
like
dominated.
Free solo type of climbing.
Not that hard. I was still climbing with ropes and gear and placing pieces. Yeah. Did some big climbs for sure.
Awesome.
But yeah, I was not free soloing. Well, I did it. Yeah. But really got an appreciation for geology and wanted to learn more about the rocks I was climbing on. So I started taking just some geology classes for fun. And then turned out I really liked science. And geology was an interesting avenue into science because it kind of encompasses almost every different aspect, from chemistry and physics to math and everything in between. And I was like, oh, I kind of like science. I'm pretty good at this too. And so I started taking some math courses, and I was like, oh, I'm pretty good at math too. This is fun. And ended up changing my degree from risk management and international affairs to geology and chemistry. So very, very big switch over. And yeah, I fell in love with it and started working at the National High Magnetic Field Laboratory, where I was working on meteorites, specifically like early cores in the solar system, where we have these planets that didn't quite form. And so I was working a lot with the metals of these cores. And that led into a love of cosmochemistry. And I've always been a really big space nerd as well. So that was really fun to go down that path. And from cosmochemistry, into analytical chemistry, and then going to do my graduate work after working at the National High Magnetic Field Laboratory in the University of New Mexico, again in cosmochemistry, but more on the stable isotopes side of things, where you're telling really big stories. Yeah.
Say that loud one more time. National Hybernetic? What was it?
High magnetic field
Oh, high
laboratory.
magnetic. Okay. I'm like, I've never heard
Sorry,
that word
sorry.
before.
Yeah,
Cool.
yeah.
Okay,
Basically, all
cool.
the biggest magnets in the world are there, so you can
Okay.
do all these fun experiments, and it's a really cool group of people.
Okay.
Really cool, cool national lab. Um, yeah, and then from there, I went to go into more cosmochemistry on the isotope side of things, where you're analyzing micrograms of material and telling stories about the solar system. It's a really fun, creative science place to be in, where you get really high precision data and you get to like really draw some big stories and some big conclusions. So I got to work on a lot of Mars stuff, including work with the Curiosity rover there. And but basically, going back from that earlier point of always taking things apart, I was lucky enough to have advisors in both location, Munir Hamayan and Zachary Sharp, who, when the mass spec broke, we took it apart and we fixed it. We got to really tinker and we got to understand. And that kind of led to me being very, I guess, contrasted by using my iPhone every day and how much technology was in there. And then looking at the lab equipment I was using and being like, how is this still so stuck, so behind from the user experience to the hardware that hasn't evolved? And I was kind of becoming disillusioned with academia as well and wanted to move faster and build things, and decided to quit my PhD program, started going to government auctions and started building mass specs in the garage. And now here we are.
That's awesome. And as you were even starting your graduate work, did you have like uh, a career trajectory planned out? Like, were you thinking like, hey, like academia or like the working in a national lab, like this is awesome, I could see myself kind of doing that, or like did you have an entrepreneurial bug, like doing side hustles, and like where did like that maybe we talk about like cosmic chemistry, like what was your mix like that you were kind of thinking about in your mindset at that time?
Yeah, I'm always definitely somebody who has like a trajectory in mind, and it's always wrong. But for sure, I was on the straight and narrow, like academic path for sure. Like I was already, publishing papers as an undergraduate, was trying to involve myself in as much of the networking and community aspect as I could in academia, was, you know, really building that like resume essentially to become a professor or, do a postdoc, go through that whole line. And the more I got into it, I was like, I don't want to do this at all. And I'd always had a little bit. My mom's a business owner, started her own business, and even in high school and stuff, I always had little side hustles going. So I'd always had like an entrepreneurial, I guess, spirit, let's say, but never really acted on it in the way of like starting a company like this.
And so you mentioned mass spec. I mean, we'll go do a deep dive into that and the company in a second. But for those listening who may not be familiar with kind of what the tool is, what it does, just the general science behind it, what can you give us a quick 101?
Yeah. So we'll just do mass spec in general. We can talk about the Massbox later, and
Perfect.
kind of what we do differently. But a mass spectrometer is just a tool that we use to separate out mass, right? So mass spectrometer, we're creating a mass spectrum. And the key components to it are you need to have a source. So you need to have some way of taking an atom or a molecule, introducing it, and then ripping off an electron or giving it an extra electron. And so that's what we call the ionization source. So there's a lot of different ways to make ions, whether it's with lasers, with chemistry, with high voltage, lots of different things that we can do to basically give an atom a charge. The reason we have to give it a charge is that once it's charged, we can interact with it with an electromagnetic field. We can talk to it. We can push it around. We can focus it. We can speed it up. We can slow it down. And what we want to do is we want to take all of those atoms that we've ionized. So let's say it's a mixture of carbon and iron and tungsten. We want to be able to separate those out, because at first they're all just going to be just glob of ions, but we need to separate them out somehow and count them. And that's really what the mass spectrometer does. There's a lot of different techniques. Some are as simple as what's called a TOF, which is what we use, time of flight. So if you kick all of those atoms with a high voltage at the same time, it's like kicking a bowling ball or a soccer ball. The soccer ball is going to go very fast and the bowling ball is going to go slow. And if you kick them with the same force. And so the same thing would be true if you kicked hydrogen and uranium at the same time. Hydrogen goes really fast, uranium goes very slow. So if you give it enough time to separate and you have like a recorder at the end of the line, you'll see a hydrogen peak, and then some microseconds later, you'll see a uranium peak. And basically, you can get the whole spectrum this way. So that's called time of flight. There's other techniques which uses magnets to separate them out, like they'll deflect more or less in a magnetic field, or using rods to some really, really clever voltage games that you can play with RF frequency to separate out mass. But essentially, it's separate out mass, count the different masses, and do it in a way that is hopefully quantitative at the end of the day. I had 10 parts per million. I had 10 weight percent, right? Having a metric to say, it's not just in here, but it's in here by this amount.
Yep. And the reason you would want to do this is you want to know what's in a given material, or if you're looking at new materials, you want to sense, okay, what's this composed of? How can I use it? How much of it is it contaminated? And some of those types of use cases.
Yeah, exactly. So if we stick to the inorganic side, since we'll probably talk a lot more about that. So just periodic table elements. Yeah, whether you're reverse engineering material, you're doing R&D on something, or you're doing quality control, it's way more important now, now more than ever in the world, to really understand the chemistry of the new metals we're making, the new ceramics we're making, or the hybrid of the two. All of these different things, we want to know down to the parts per million how much carbon and oxygen are in there, how much tungsten, and correlating that with, let's say, the strength tests that you're putting these things through, and getting a much better refinement on that material characterization. And currently, there's a lot of lacking in this. It's much more qualitative a lot of the time on chemistry, because it's very difficult to do. You can either do kind of qualitative fast analysis with spectrographic tools that are kind of looking at, let's say, like X-rays or light emissions from the samples, or you can do digestion and go through mass spectrometry and get really good answers, but 4 to 5 week turnarounds and $1,000 per sample to get all the elements you want. It's kind of this dichotomy. And that's kind of where we sit right in the middle.
Okay, and let's go into that journey a little bit. What was like? So you had thrown academia out the window, like, I'm done with this PhD stuff and graduate work. What was kind of your next step? Like, where were you at, and what was your mindset?
Yeah, so my mindset was complete ignorance, because I had no idea what I was getting into, which was great place to start. So mindset was basically dealing with rocks and geology and meteorites and cosmochemistry and all sorts of other projects. It was always so difficult to do solid sample analysis. If you're dealing with liquids, it's easy, but solids were always so hard to do. And I wanted to basically make a tool that would completely change the experience of taking, like, this 3D printed part, let's say, little rocket, and within a few minutes, getting quantitative answers down to the parts per million level of what it's made of. Also getting spatial resolution out of it. And fundamentally, the reason why I wanted to have a new technology to do this was to enable a software aspect that would be completely different. Because you couldn't just, put lipstick on a pig or slap, a software Band-Aid on it. The hardware was just so fundamentally dated that the software that would be required to make it as easy as I want it to be would be nearly impossible. And that's why, a lot of it still hasn't changed. And so I knew that we needed to start with hardware to create a completely new software experience, and had a few ideas with a couple of my co-founders and I. We were just kind of like looking at what we could do, and we knew it needed to be laser based, and we had no money, and we couldn't get money because we didn't have a proof of concept. So we were in this like catch-22 of starting a company. So we started going to, there's great government auctions that they just get rid of everything. And so we would just start buying like massive lasers and old mass specs and start taking little pieces off of all of them to make this like Frankenstein prototype. We also had some help with some other friends that like gifted us some like certain parts off of old laser ablation systems. So we kind of cobbled this thing together, and it took a while because we were kind of having to like support ourselves, and also on the off time, like put together, just enough of a prototype to prove that this idea could work to then go get money in partnership and all of that.
And what were you doing on a part-time basis?
It was glorious work. I was taking care of rental properties, so toilet breaks, got to do some painting, all of that kind of stuff. And then also my partner is a farmer, and she was working at a startup that was doing like indoor agriculture, so like vertical farming. And so I was like helping out there and delivery driving and basically anything I could do for work at the time that would still give me the flexibility to work in my off hours.
Yeah, I was the same when I started my company. I was doing, I think I made $12,000 a year in 3D printing stuff, and the rest of the time I was doing college recruiting for companies.
Nice.
Got to do what you got to do. I like it.
Exactly.
So, and where were you at this time? So you grew up in Florida, then you were in New Mexico at this lab. So where are you in geography wise?
Yeah, so I was in New Mexico when we first started. And basically we realized pretty early on New Mexico is not going to be the place. New Mexico is an amazing place with just brilliant people and good infrastructure for a lot of things, but it just doesn't have the funding and just the capital in the state. And so I made the decision when kind of looking at the matrix of where do you go? It's like San Francisco, New York, Boston, or Denver.
Yeah. And
Denver sounded a lot better. So we decided to go to Denver, and it ended up being a really good call. It was kind of, Denver had a pretty steady growth in the startup scene, but it really started exploding about the time that we moved up here. We have Denver Startup Week, and there's just been a huge capital influx up here, and a lot more funds, a lot more opportunities. It's been a really good place to start a company.
Nice. And so, I mean, and then especially the hardware company too, like software, like people are used to valuing like what's your SaaS business model, how many recurring revenue customers are you going to have. But with a hardware piece, like someone's got to manufacture it, like it's longer sales time, like you have to also probably do software alongside your hardware. And so how was it? I know in Chicago, I mean, I'm actually based here. I'm at a hardware incubator in kind of downtown, but those aren't unique. And so what was the ecosystem like for kind of getting money as a hardware company some of those early days? What was your strategies? Were you doing grants? Were you doing VC? Like what was your approach?
Yeah, raising money as a hardware company is difficult. Yeah, because people just, like you said, they don't have the metrics for it, right? They're like, oh, how many users do you have? 0. Oh, great. Why are we talking? No, it's like, no, this is different. Yeah, it's still very difficult. And also this is like post Theranos as well, where hardware got like a really bad name and everybody wanted to de-Theranos you. And it's like, yeah, but we still have to like work through this early stage. We'll do it in a much more ethical way than Theranos. We're not, but hardware kind of took a hit there for sure. And most funds theses tend to be SaaS and SaaS within a specific environment. So like, oh, we like it. We think it's a cool idea. There's definitely a market. Good luck. It's just like not a fit. Yeah. So it took a long time. So what we ended up doing was we knew we needed to kind of get some technical due diligence, right? And so we actually reached out to one of the world's like leading mass spectrometer manufacturers for this specific type called TOF, time of flight that I talked about. And I reached out to them, and Mark Gonig and Katrin Fuhrer, they're the founders of TOFWork, and they really liked the idea, and they believed in what I was doing, and they said, we'd love to help you. And we formed a JDA with them. So they were actually like kind of saying like, hey, we think this is a good idea. We've seen the preliminary stuff that they've done. And that gave our initial investor enough confidence to say like, okay, yeah, I'll write $180,000 check and let's just get a prototype built and see where it goes. So it was kind of just trying to find that technical validation that was faster than going through the process of going through a phase 1, phase 2 SBIR at the time. Maybe there was a path where we could have done that differently as well, but it just wasn't my expertise. We now have Ellen who crushes through SBIRs and we love them. But to start off with, it was definitely very helpful just to find an expert in the field that believed in us enough to kind of like, get on the cap table.
Yep. And so what is I want to go into the product a little bit and kind of what's it look like? What does it do? What are kind of the big differentiators?
Yeah. So when identifying what hardware we were going to develop to make this, this instrument that was going to be the best in the world for solid sample analysis, we knew it had to be able to be lower cost than buying 3 instruments, which was an easy bill to fit. It had to be able to sit onto a desktop. It needed to be touchscreen, and it needed to be one power cord out the back. No complexity. You don't need a clean lab environment. And so what we netted out on and what we invented and created all of our technology around is this idea of using 2 lasers. So we had a 3-inch by 3-inch sample tray that you can put anything that's solid and flat on, right? Loaded into our chamber. It basically takes an image of the entire stage. You use that to navigate around with, and you're just selecting points of where you want to analyze. And at every point, what's going to happen is a primary laser is going to come down and ablate a little bit of material. You can think of it like, when you drill cement and it makes a dust cloud, we're kind of doing that with light. So we're focusing light really intensely and removing a little bit of material. Oh yeah, you know all about this. It's similar to like 3D metal printing, but instead of like melting, you're like vaporizing. So UV instead of infrared, you're just kind of like breaking apart all these atoms. And so you have this neutral particle cloud that's formed above the surface. And a lot of techniques had stopped in the past because when you make this ablation, and you've probably seen this as well, you get this little plasma that forms. And a lot of other techniques would utilize this plasma either by looking at the spectrum emission of the plasma, like we do for stars or something like that, and looking at the elements that way, or by taking those primary ions from the plasma and putting those into a mass spec. And the difficulty was it's really good qualitatively to say what's in something, like, hey, there's definitely sodium in there. But it's very difficult to say there's 10 parts per million sodium in there. And then it's even harder if you have materials that aren't perfectly matrix matched. So quantitation just became really, really difficult, and it's why it didn't industrialize. Well, what we said was that neutral particle cloud that's formed is much more stoichiometrically representative of the solid it came from than that plasma is, because that plasma is a very energy limited environment and you end up in this multivariate space. So let's look at this neutral particle cloud. So then we take a secondary laser, which is another UV laser, and we're just blasting it with tons of power. And what happens is you end up doing a process called multi-photon ionization. Basically just 2 photons of light excite an electron twice. So gets excited, moves up an energy level, gets excited again. And now it's far enough away from that nucleus that it's effectively separated. You've created an ion-electron pair. And so that's what we use to make our ions. And we're getting our ions from a better source of material. And we're also flooding the ionization process locally there. And what that helps us with is that kind of matrix match standardization that I briefly talked about. It means that things are going to behave more similarly than if you had 1 part per million nickel or 1 weight percent nickel in an iron. They're going to ablate very similarly. They're going to ionize very similarly. And that allows our instrument to be very linear across a lot of orders of magnitude. And the reason why this is important is that, once we go through the time of flight mass spectrometer, we count them. We want that software experience to be so removed that you don't feel like an analytical chemist. Mm-hmm. You just feel like you're using a tool. And that means our software life is so much easier because it's like all of the mass spectrums are very clean. The integrations are very easy to do. The standardization is very easy to do. So we get to deliver that experience that you're just following a path. You're choosing points, you're pressing go, you're applying a calibration curve, you're printing it out. You're done. So yeah, that's basically the product. I can go into more detail or see where you want to go from there.
And what are some of the early customers or like other early use cases that people are like, hey, like this makes a lot of sense. We want to try this and kind of take it around the basis for a spin?
Yeah, so additive manufacturing is a huge one for us because it's kind of the Wild West in additive manufacturing right now, both from like materials that are being developed and explored. And, a lot of it's kind of ad hoc chemistry, just like, hey, this works, great, do that. And also the quality control parameters of what it means to reuse a powder, right? From a chemistry perspective. What does it mean to look at a final part chemically, in 2 or 3 dimensions as well, looking at homogeneity. Same thing on the powder that's going in. So we're really, really excited to be involved in the additive manufacturing community. We actually just received a grant from NIST as well to help kind of set up a lot of these standards for certain materials, so like aluminum, stainlesses, GR COP, a lot of the kind of, I would say, routine materials there. We really want to set an easy standard using our technology to get some better quality control in the field. So we're really, really excited about that application across a ton of fronts. And then we're also selling into, Los Alamos with the IAEA doing nuclear work as well, or in batteries too. So we kind of have markets that we're exploring, I would say, and we're setting the groundwork for. But going into the end of this year and next year, most of our marketing and most of our applications development is on additive manufacturing.
And what's the size of the company now?
So we're 15 full-time people and like a few more with contractors, but we're looking to probably double next year.
That's fantastic. And so I'm always interested in additive stuff. I mean, like when you take a part like you have in your hand, a rocket chip or an actual part, do you section that, polish it, and then put it into your system, or are you able to take, you said it needs to be flat, and is it thin as well, or does it just need to be flat?
Less than 30 millimeters. So you could take this rocket and put it in just like this, and we would be able to analyze, the top part of this fin right here.
Got it.
I know this is a podcast, so probably hard to.
It'll be on YouTube, so it's all good.
Okay, good. Yeah, so it just needs to be. It doesn't need to be polished. It just needs to be flat, and we can't analyze anything lower than the highest piece as well, right? So we have about less than a millimeter of tolerance between the samples. So if you put 9 samples in the holder or 14 samples in the holder, they need to be plus or minus less than a millimeter than each other, and that just comes down to like the focal length of the laser and kind of some other constraints we have.
And I'm really interested in your idea about usability and kind of getting actionable data. So when you kind of started to build the machine and the software interface, kind of who did you have in mind as your user / customer? Like what problems were you, you probably had a lot of these when you were doing some of your research, but like what did you have in mind as you were designing the tool itself?
Yeah, it's interesting because like I didn't come from industry, right? I was coming from academia, but the problems were still the same. And we also dealt with a lot of industry companies, even in academia, because they couldn't do it internally. And so most of my time as a grad student, as a cosmochemistry grad student, was analytical chemistries and basically learning how to fight mass spectrometers. So what I wanted to think about from the user perspective was like industrializing mass spectrometry, taking it out of the analytical chemist's hands and out of the lab requirements so that more people could get the data they wanted on the shop floor, on the factory floor, in an office. It can go anywhere. And so I didn't want you to have any background. You needed to know what answers you were looking for sure. So as a mechanical engineer, let's say, right, you're like, okay, I want to at least make sure that this stainless steel is within spec for what I'm getting from the manufacturer. And having that process be very easy for you to get to. Because if you decided today that, you know what, I want to nail down the amount of tantalum that I'm putting inside of something, right? It's going to take you a while to figure out what labs are you going to use, what techniques are they going to use to analyze it, how are you going to actually standardize it if you're making something new? They're going to say like, oh, I've never seen this before. We can't guarantee the results to a certain spec. Or they might say that they're going to and they're lying to you, which happens all the time. And then you'll send it out to another lab and get a completely different answer. So really it was like trying to, science simplified is our kind of like slogan, right? It's trying to take that entire experience from, I want to know how to standardize the amount of tantalum to the next day, you're setting up a routine to do that.
And how do you calibrate your system? Like I mean, that's probably always a question in terms of any new piece of test equipment and approach. Like we had I don't know if you know there's a company called Plastometrics that has like a little desktop in mechanical indenter for metals. And so they're coming up with a new testing platform for mechanical testing, and probably similar to yours. There's always a question of, okay, especially when it comes to additive, people are already hesitant to use a new technology to manufacture something. They're even more hesitant to use new technology and something that's being tested in a new way or on a new machine. So how do you overcome some of those hurdles that I always see in the industry, and I'm sure you probably have discussions on a daily basis?
Yeah, no, you're 100% right. And it's actually like, surprisingly, it's one of the reasons like we're in additive as well. Like one of our initial markets we were going after was oil and gas. And there's no way you're getting anybody to use new technology in oil and gas. They're like, well, I've never been fired for doing it this way, so why would I change now? Right. It's kind of the mentality. It's very slow to adopt. Whereas additive, because it's new as well, and because there's not standards, there is a little bit more flexibility, and there's a little bit more, I would say, room for new technologies to grow as well. So, one of our partners and customers, Elementum 3D, they immediately saw the value because they're a powder manufacturer. They're trying to do internal QA QC to cut down on their OpEx for when they're shipping out powders to customers, also increase throughput on their R&D as they're developing new materials, and they're spending $1,000 a sample. So it really limits what they're doing. So they were willing to say like, hey, let's take a risk on a new technology here because the upside benefits relative to what's out there really outweigh the risk. Now we still had to do a lot of proof here. Like we do what we call, digital demos or in-person demos where you'll send us something that generally you know the answer to, and we might ask for like, well, do you have a reference material for it too? And we'll give you the answers, and they say, yep, you got the right answer. So it's like we do a lot of justification of like, hey, we got the same answer as this, or we published where, we'll get the same answer as a NIST calibrated standard, or we participate in ASTM studies as well, where they'll send out blind samples. So we're trying to do a lot of validation with this, but it is that like chasm of adoption for sure, where you need enough out there and enough customers using it in a real world environment long enough to where you'll get like the, Lockheed Martins of the world saying like, you know what, we need to have 5 of these, right? Yeah. So we're kind of right there where we're finding early adopters who really want to, bring in new technologies and are providing so much value to us in the way of marketing more than anything we could publish. It's when, Jeremy says like, this thing is great at Elementum 3D. That's a huge deal for us.
For sure. And so if people want to see the technology, I know you're going to be at some trade shows upcoming next year in 2023. So you want to tell us a little bit more about that, or if like as people want to learn more, where do they go? What can they come visit? Can they knock on your door in Denver?
Yeah, absolutely. So we'll be at the Military Additive Manufacturing Conference, AMUG, and Rapid TCT. I know upcoming next year. So come by the booth, come visit us. That'd be great. If not, also reach out, on the website if you want to schedule a demo. We have a really great applications and business development team. We'd love to hear about what you want to do and to shoot some stuff with lasers. It's really fun when people come into the office and touch it. That's when you get the moment of like, oh, I need this, right? Not as like, oh, this is a nice to have. Especially when we do fun things. Like we just had an additive manufacturing company in last week that was looking at chemistry in the pores, and they'd only done like digestion before. So they get this bulk composition of like all of the powder. And they're like, well, we think these are the contaminant elements. And then we do a chemical map and we look in the pore space and we're like, yeah, your contaminant elements are right here. And like when you get that kind of visceral experience of like the questions you've been answering are answered in this really nicely presented way, it's fun. So we always recommend people just come up to Denver, come shoot some stuff.
And can you do both metals and polymers or ceramics, really anything?
Yeah, we do ceramics. Polymers, we haven't done as much work on. We can shoot them. We've done a little bit of like kind of looking at it. mostly from an elemental side again. So if you're really concerned about like the amount of iron, or actually we do have a customer that is interested in like certain elements in their polymers, we can definitely do that. In the future, we also will have the technology to do both, elemental and organic analysis in the same analytical session. But right now we're just focused on elemental work. But yeah, we can do polymers, just hasn't been a big application focused.
Right on. And so I like to end the podcast with going back to the personal questions. We're kind of compiling a mini 3 Degrees discussions book club. So is there a favorite book or that you've read over the last year, or meaningful book that you've read in your life that you'd like to share with the audience? We're kind of compiling a list here. We'll be put on the website as well.
Yes. Well, okay. We'll go from a non-sci-fi perspective. Feynman's Rainbow is like one of the best books. I'm sure that's a highly recommended one. But what a great book. Richard Feynman was just such a incredible character and polymath. And yeah. So, and also any of the books that are kind of derivative about his life are always fascinating to read. From a sci-fi perspective, because I'm a big sci-fi nerd as well, Red Rising series is amazing.
Okay. Awesome. We're gonna add it to the list. So awesome. Well, Jeff, I really appreciate you taking the time today. Everyone should go and check out kind of all the cool work you're doing. If you're in Denver, drop by, and we'll certainly see you in February. It'll be a break for me from the Chicago winter down in Orlando, so I'm gonna like it. But,
awesome.
Cool. Well, thank you very much, and we'll talk soon.
Yeah, thank you so much. Cheers.